Hey everybody, we are on to 4.6, which is something called related rates. And we start off with, what is a rate of change? Well, remember, change in y over change in x. That's our formula for slope. That is the average rate of change of y with respect to x. And then from there, we were able to get to dy by dx, which is the instantaneous rate of change of y with respect to x. Okay, so the instantaneous rate of change of y with respect to x, and we could calculate that for any particular point. And then we can apply this idea to velocity, which is ds by dt, which is the rate of change of position with respect to time. And we could do acceleration, which was dv by dt, which is the rate of change of velocity. With respect to time. Okay, and we can go a little bit further. We could use capital V to stand for volume. And this is dV by dt. This is the rate of change of volume with respect to time. And we could even do like a dr by dt, which is the rate of change of the radius with respect to time. Okay. So WRT means with respect to. Okay, so let's look at some formulas. Area. The radius r and area a of a circle are related by the equation a equals pi r squared. That's the area of a circle. We are going to write an equation that relates dA dt to dr dt. Okay, so we start with area equals pi r squared. And basically what we do here, guys, is you treat all of your variables as functions of time. Okay, and so the radius of a circle can vary, so r can vary. And if the r varies, different radiuses give you different areas. So as r varies, a varies. Okay, and we can treat these as functions with respect to time. And what you do is you differentiate them normally, and then because we're treating it as a function of time, we have to write dA dt beside our a derivatives and dr dt beside our r derivatives and so on. It's kind of like implicit differentiation. When we did like a y derivative, the derivative of y squared, we were treating y as a function of x, and we said that this was 2y dy dx, the chain rule part, right? So if we treat a as a function of time, the derivative of a itself would just be 1, and then you put dA dt beside it. And over here, pi is a constant. The derivative of r squared would be 2r. So we'll have a 2 multiplying down in front. The power on the r goes down by 1. And since r is a function of time, we write dr dt beside it. So the change in area with respect to time is given by this formula, which involves the change in radius with respect to time. Okay, and when you have just a single variable like a, you don't have to put the 1, right? Because you have the dA dt beside it, so it's 1 times dA dt. It's just like the derivative of x, right, is 1. Because it's x to the power of 1, and the 1 would go down in front, and then it becomes x to the 0, which is 1. Okay, so that's why this holds true. Alright, the side S and area A of a square are related by the equation A equals S squared. Write an equation that relates dA dt to ds dt. Okay, so this is just a single variable, so its derivative is dA dt. S squared, the derivative is 2s, right? And since s is a function of time, we write ds dt beside it. Okay, so the area of a square changes as the side length s changes. Alright, how about volume? The radius r and volume v of a sphere are related by the equation, that should be v equals 4/3 pi r cubed. Write an equation that relates dv dt to dr dt. So we've got v equals 4/3 pi r cubed. The v is kind of like just an x sitting there, right? The derivative of x is 1, so the derivative of v is 1, but since v is a function of time, we would go 1 times dv dt. And over here, 4/3 is a constant, pi is a constant, r cubed, so the 3 multiplies down in front. 3 times 4/3 pi would just be 4 pi, and then the power of the r goes down by 1, and then dr dt. Example 1 is exactly like that volume thing we just did. It says a balloon is filled with air. What is the relationship between the rate of change of volume and the rate of change of radius? So you have to assume that it's a spherical balloon, and the volume of a sphere is 4/3 pi r cubed. And so then we would get this again for rate of change of volume with respect to time. Okay, so let's check out example 2. What is the rate of increase of the volume of a balloon when the radius is 3 centimeters and the radius is increasing at a constant rate of 2 centimeters per second? Okay, and so to do this, guys, we're actually going to use this method which is called find, when, and given. And so let's draw a little picture. You have to imagine this is the balloon, and we have to assume that it's spherical. Okay, and as that radius increases, so will the volume. Okay, so you're adding more air into the balloon. It's going to make the radius bigger and the volume bigger. Okay, so we're going to do this process of find when. Okay, so like at what instant and given. And so it says, what is the rate of increase of the volume of a balloon? So they want us to find the change in volume with respect to time. When the radius is 3 centimeters, so at the instant that we hit r equals 3 centimeters, and the radius is increasing at a constant rate of 2 centimeters per second. So the given is that the change in radius with respect to time is 2 centimeters per second. Okay, so there's the initial setup. You then have to come up with an equation that relates all of your variables. And so we're talking about volume and radius. Okay, and we're assuming that this is a spherical balloon. So the volume of a sphere is 4/3 pi r cubed. Okay, and they want us to find dv dt, so we will differentiate this equation with respect to time. So you go dv dt equals 3 times 4/3 is 4. We still have the pi, r squared, and then dr dt. And we want to find dv dt. It's by itself already, so that's great. And so you go 4 pi. We want it at the instant that the r hits 3 centimeters, so that goes in for r. And we know that the radius is changing with respect to time by 2 centimeters per second. Okay? So 3 squared is 9. 9 times 4 is 36. 36 times 2 is 72, and then we have the pi there, so we could write it in terms of pi, an exact value, 72 pi, and notice I have centimeters squared times centimeters, so that's going to be centimeters cubed per second, which is a rate of change of volume with respect to time. Remember, volume is in cubic units. Okay, so that's how quickly the volume is increasing right at the instant that the r hits 3 centimeters. Okay, and what is 72 pi? Just to give you some perspective. 72 pi. Okay, 226.2 roughly cubic centimeters per second is how quickly the volume is changing at that instant. All right, let's try another one here. Example 3. The radius of a circular disk is increasing at the rate of 3 centimeters per second. So circular disk, and we're going to have the radius increasing. What is the rate at which the area is changing when the radius is 4 centimeters, I guess that should say. Okay, so we'll set up our little process, find, when, and given. And they want us to find what is the rate at which the area is changing. They want us to find change in area with respect to time. When the radius is 4, and I'm going to assume that that's 4 centimeters, right? Because of the 3 centimeters per second. Given the radius of a circular disk is increasing at a rate of 3 centimeters per second. So the change in radius, that's a rate of change. Change of radius with respect to time is 3 centimeters per second. Okay, so then we have to come up with an equation that relates A and R. Circular disk, area, radius. The area of a circle is pi r squared. Okay, differentiate both sides with respect to time. So dA dt is equal to 2 pi r times dr dt. And they want us to find dA dt. Notice it's by itself in the equation already. That's not always going to happen. We might have to do some algebra first. Okay, but in these first few examples, we've got what we want to find by itself. So you go 2 pi. We want this change in area with respect to time at the instant that the radius is 4 centimeters. And the dr dt is 3 centimeters per second. Okay, so we end up getting 2 times 4 is 8, times 3 is 24, so we're going to get 24 pi, and we have centimeters squared per second. It's the change in area with respect to time, and you can see centimeters squared are area units. Okay, so the area is increasing by 75.4 square centimeters per second right at that instant that the radius is 4 centimeters. Okay, example 4 says find the rate of change of the area of a square. Area of a square when the sides have length 3 centimeters and the sides are increasing at the constant rate of 9 centimeters per second. Okay, so we have a square. S. We will do this find when given. Find the rate of change of the area of a square. So change in area with respect to time. When the sides have length 3 centimeters, so when S equals 3 centimeters, and the sides are increasing at the constant rate of 9 centimeters per second, change in side length with respect to time is 9 centimeters per second. Okay, so there's the initial setup. Then we have to come up with a formula relating A and S. The area of a square in terms of its sides is side squared, S times S for the area of a square. Differentiate both sides with respect to time. That would be 2s and then ds dt. We're treating it as a function of time. And we want to find dA dt. Again, it's by itself. 2 times, we want the s to be at the instant of 3 centimeters. And ds dt is 9 centimeters per second. 2 times 3 is 6. 6 times 9 is 54 centimeters squared per second. All right, let's get on to example 5. It says water is being poured into a container in the shape of a cylinder 4 centimeters high and 2 centimeters in radius at a rate of 6 centimeters cubed per second. At what rate does the surface of the water rise? Okay, so we're pouring into a container in the shape of a cylinder. Okay, we have a nice cylinder here. Okay, and water is being poured in like this. And let's just say that it's got a certain amount of water in here. Some nice red water. Okay, and let's write down our process. Find when and given. Okay, and so notice the question says, at what rate does the surface of the water rise? So we have to come up with a description of that, and that's the height of the water. Okay, so water like this is being poured in, and the height is increasing, right? At what rate does the surface of the water rise? So we want to know the change in height of the water with respect to time. Okay. Now, they don't specifically say when, but we know that the height of the cylinder is 4 centimeters. Okay, and the height of the water is changing. But I guess it can't go beyond 4 centimeters because that's the height of the cylinder. And then we've got that the cylinder is 2 centimeters in radius. And if you look at a cylinder, you have to ask yourself, does that radius ever change? No. As the height of the water increases, that radius will always be 2 centimeters. So the R is 2 centimeters. Okay, and what's given to us is the rate of volume going into the cylinder. Okay, water is being poured into a container in the shape of a cylinder 4 centimeters high and 2 centimeters in radius at a rate of 6 centimeters cubed per second. So that's the change in volume with respect to time. 6 centimeters cubed per second. Okay, so now we have to relate volume and height of a cylinder. The volume of a cylinder is pi r squared h. Okay, and all of these variables we're treating as variables with respect to time. So we've got volume, and we have radius, and we have height. which means, guys, that we're actually going to have to use the product rule for this when we do the derivative. So when we take the derivative with respect to time, the derivative of v is 1 dv dt. We have a product, a u times v, where we're going to have to go u prime v plus u v prime. Okay, so the derivative of pi r squared is going to be 2 pi r dr dt. Okay, and then you're supposed to multiply that by the regular second function plus the normal first function times the derivative of h. The derivative of h with respect to time is 1, and then dh dt. Okay. So it seems like we have a whole lot of extra variables. But the good thing about this is, if we look at a cylinder, again we have to ask ourselves, does that r ever change? When we are pouring water in here, does the r ever get bigger or smaller? No. Okay, as you go up the cylinder, the r always stays the same, so the change in r with respect to time is 0. Centimeters per second or whatever, right? Okay, so dr dt is 0, and dr dt is right here. 0 times all of this other stuff, that's going to knock off that whole term. So the change in volume with respect to time is equal to pi r squared dh dt. The height certainly changes, right? The height of the water changes as you pour water into a cylinder. We do that almost every day, pouring a glass of water. And depending on your glass, the radius may change as well, or it may not. Okay, so now we're in business. We know that it's when r equals 2, okay, because r is always equal to 2. We're looking for dh dt, so we're looking for this one. So we just have to divide both sides by pi r squared. Okay, so dh dt is equal to dv dt divided by pi r squared, and dv dt is 6 centimeters cubed per second divided by pi times r squared, and the r is always 2 centimeters, and we are good to go. So we're going to have 6 centimeters cubed per second divided by 4 pi centimeters squared. Okay, and of course 6 over 4 can be broken down to 3 over 2, and we still have that pi on the bottom. Centimeters cubed divided by centimeters squared is just centimeters, so centimeters per second. Okay, which would be a measure of change in height with respect to time. Okay, so that's a little bit more of a tricky one. Let's try example 6. Water is being poured into a container in the shape of a rectangular box with square base, 4 by 4 by 12 centimeters at a rate of 50 centimeters cubed per minute. At what rate does the surface of the water rise? Okay, so we've got this box. Okay, like this. And the water is going in like that. It's going to make a nice block of water. Like so. Okay. Alright, so this is a rectangular box, a rectangular prism, and we have a volume of water going into the box, and we're interested in at what rate does the surface of the water rise. So again, the height here. And the formula for the volume of a rectangular prism is volume equals length times width times height. And they have told us that it's a square base, so we got 4 centimeters here, 4 centimeters here, and the full height is 12 centimeters. And if you take a look at the red water here, hopefully you'll agree with me that the length and the width don't change. Right, the length of the water and the width of the water will always remain at 4, and just the height will change as the water creeps up this rectangular box. So our volume expression can then come down to 4 times height. So volume is equal to 16 times height, volume of the water. And I guess really we should have done our find when given. At what rate does the surface of the water rise? So again, find change in height with respect to time. Okay, it doesn't really say when, but we know that L is 4 centimeters and W is 4 centimeters. Given water is poured into this box at a rate of 50 centimeters cubed per minute, the change in volume with respect to time is 50 centimeters cubed per minute. Okay, so we've now set up our formula relating volume and height, and then differentiate both sides with respect to time. So we get dv dt equals, the derivative of 16h is 16, and since h is a function of time, go dh dt. And then we just need to get dh dt by itself. Divide by 16, divide by 16. So dh dt is equal to dv dt divided by 16. The dv dt is 50 centimeters cubed per minute. And the 16, it actually came from that 4 times 4 length and width. And notice the length and width are both in centimeters, so the 16 is 16 centimeters squared, and that's going to make sense for our units. $50 divided by 16 is that. Let's go math. Fraction that. 25 over 8. Centimeters cubed divided by centimeters squared is centimeters per minute, which is the change in height with respect to time. All right, and finally, example 7. A conical reservoir is being filled with water at a constant rate of 6 cubic meters per minute. If the reservoir is 3 meters deep and 8 meters in diameter at the top, find the rate at which the surface level of the water is rising. At the instant the depth of the water is 2 meters. Okay, so conical reservoir. Conical means like a cone, right? Okay, a nice conical reservoir like this. Draw that particularly well. It is 8 meters in diameter. Maybe should have kept. Sorry. Let's keep this blue. Eight meters in diameter. And the height will be like that. And it says it's 3 meters deep. So let's do our find. When and given. Find the rate at which the surface level of the water is rising at the instant the depth of the water is 2 meters. So we want to find dH dt. Okay, so again, we've got water pouring in here. And it will start to pool like this. Okay. That's the height of the water. And this is the radius. Okay, so find the rate at which the surface level of the water is rising. At the instant the depth of the water is 2 meters. So the when is when h is equal to 2 meters. And the conical reservoir is being filled with water at a constant rate of 6 meters cubed per minute. So we are given the change in volume with respect to time, which is 6 meters cubed per minute. Okay, so we're going to have to come up with a formula that relates volume and height within a cone. And the volume of a cone is 1/3 pi r squared h. So there's our formula. And we are again going to have two variables on this side, which means product rule. And the thing that separates this question from that cylinder one before, guys, is that the h changes. The height of your red water is going to change as this water is pouring in, but so does the radius. The radius changes too because this is a cone. And so you can see that as this fills up, if we got up to here, look at my radius of my water. The radius changes too. Whereas with the cylinder, the radius didn't change and we got the dr dt was 0, and that kind of helped us cancel some things. Okay. Okay, but in this situation, h changes and r changes. And I'm just going to pause for a second here, and I'll be right back. All right, I'm back, everybody. Sorry about that. Okay, so we were talking about how this question is a little bit different than the cylinder one because R changes and H changes. And so because we know something about H and they haven't really said much about R, what we're going to do is we're going to try to eliminate the variable R. And we're going to do that by using similar triangles. Since this whole diameter is 8 meters, I'm going to split this into 4 meters and 4 meters. And notice that we have a nice 90-degree triangle right here. We've got 4 meters like this. And we do know that the height of this conical reservoir is 3 meters out over here. So this is the 3 meters. And there's our 90-degree triangle. Okay. And then I'm going to drag out this little red one right here. Which is labeled as H and R, right? H and R, and they've got 90 degrees in common. They have this angle where it's the same angle for both of them, which comes from right there. And then this angle here is equal to this angle by either third angles, or you can see parallel lines, corresponding angles, however you want to call it, okay? And when you have two triangles that have equal angles, those are called similar triangles, and the sides are proportional. So, if I were to do radius divided by h in the little triangle, that will equal radius divided by h in the big triangle. And what we can now do is multiply both sides by h, and we get an expression for r in terms of h. And I'm going to take this and I'm going to plug it right here. And so our volume will be 1/3 pi. And instead of r squared, I'm going to have 4/3 h squared times h. And now that will kind of help us with our two variable problem. Okay, so what are we going to get here? 4 squared is 16, so on top I've got 16 times pi times 1, so I have 16 pi. And I also have h squared times h, which is h cubed. Okay, so there's the top situation, and the bottom we've got 3 squared is 9. Okay, from the brackets, 9 times 3 is 27. All right, so there's our expression for volume. And now we want to differentiate both sides with respect to time. 3 times 16 pi over 27. 3 times 16 is 48, so we'll have 48 pi over 27. That's going to go down to h squared, and then have dh dt. And we ultimately want to get dh dt by itself. So I'm going to divide both sides by all of this stuff. And now we'll plug everything into this expression here on the left. dV dt is 6 cubic meters per minute. Change in volume with respect to time. We have 48 pi. over 27, and then times the h squared. Okay, and it wanted to know Find the rate at which the surface level of the water is rising at the instant the depth of the water is 2 meters. So when h hits 2 meters, we'll have that squared. So I have 6 cubic meters per minute on the top divided by 2 squared is 4. 4 times 48. 4 times 48 is 192. So we have 192 pi and then over 27, and that is meters squared. So this will be 6 cubic meters per minute. When you divide by a fraction, you can multiply by the flip of the fraction. So 27 over 192 pi. And since I flipped the fraction, that will end up on the bottom, right? The meters squared. So here's what we're going to get. I'm going to keep the pi on the bottom just so we keep it in terms of pi. But let's see, on the top, we're going to have 6 times 27, and then we're dividing that by 192, and then I'm going to go math and fraction that. So 27 over 32. And we still have that pi on the bottom. Okay, and meters cubed divided by meters squared is meters per minute. Okay, and that is the change in height with respect to time of the water in this conical reservoir. Alright guys, so that's how you do example 7, and the assignment says Rates and Related Rates Assignment 1 sheet, which is right here. Okay, so I would encourage you to give these a try. The answers are down below, except I should tell you that this one here, that's not quite right. It should be -1 centimeters per second. Okay, so give those a try, see if you can get those answers. Let me know if you have any problems, and I will talk to you soon.